Okay, this video is for AP Calculus BC, and we're doing the second half video for partial fractions expansion. The entire idea is explained in the first video. You just need to look at this if you want additional examples, and we'll finish with one really complicated one if you just want to see how far this idea can be pushed. So for this, for more practice, maybe try pausing the video and then trying it yourself, and then unpause the video and see if you got this correct. For this problem, I would start by factoring the denominator. So we've got x squared plus x minus 2, and that factors into x plus 2 times x minus 1. And so if I factor that into that, then that means that the fraction 5x plus 3 over this is factored. That means I have two linear non-repeated linear terms in the denominator, so that's going to be a over x plus 2 third denominator. So this a is going to get multiplied by the x minus 1 denominator and the b by the x plus 2. So I have a times x minus 1 plus b times x minus 2 equals the current numerator 5x plus 3. I don't bother with the denominator at this point because everything would have the same denominator if you multiply top and bottom by these. So getting rid of parentheses, ax minus a plus bx minus 2b equals 5x plus 3. Gathering like terms, we have a plus bx's on the left, and we have a constant of negative a minus 2b. On the right, we have 5 x's and a constant, which is 3, matching up the x's. We get a plus b is 5, matching up the constants. Negative a minus 2b is 3. If I solve that system by elimination, these cancel. We have, let's see, negative 1b equals 8, so b would be negative 8. All right. Not matching my answer key. Right. That's right. No, that's negative b would be 8, so b is negative 8, and then that means that a minus that 8 equals 5. A would be 8, it's 13. It's 13, okay. Oh, I see the problem. I did introduce an error. Let me fix that. Make sure it's correct. And this is multiplied by x plus 2, not x minus. I'm going to go back and repeat that. Okay. So this would be a times x minus 1 plus b times x plus 2 equals the numerator of 5x plus 3. So we have ax minus a plus bx plus 2b equals 5x plus 3, which is a plus bx's plus a constant of negative a plus 2b. That was the sum there. And then we have 5x plus a constant of 3, matching up the x's. We have a plus b equals 5. Matching up the constants, negative a plus 2b has to equal 3. We can solve with elimination. The a's cancel, and we have positive 3b equals 8. So b is 8/3 actually, if that matches my key. And then a plus that 8/3 b constant equaling 5. Tripling everything, 3a plus 8 has to equal 15. So 3a has to equal 7. So a would be 7/3. And that means that this is 7/3 over x plus 2 plus 8/3 over x minus 1. Which means in the original problem, you can have a separate integral for each of those. So I'm going to just go straight to this. This is equal to 7/3 times the integral of 1 over x plus 2 plus 8/3 means the integral 1 over x minus 1. And then that would just be 7/3 natural log of x plus 2 plus 8/3 natural log of x minus 1 plus a c and then a 1. Realizing we can put an example in with more complicated factoring. So I'm going to replace, let's see, is this the one I want to do? Yeah, instead of having just another one like this, let me change this a little bit so that we can see something else that can happen. So let's say we have this problem, but I'm going to change the denominator. Instead of being that, let's make it this problem. 3x minus 5 over, I'm going to go ahead and factor it. I want this to be 2x plus 3 times x minus 1. Say it's already factored, which means that that would have been something with a leading 2 here. Like this would be, it would have appeared like this. That would be 2x squared, and then 3 minus 2 would be 1, so plus x minus 3. So if we had this problem, well, when we factored, we had 2x plus 3. There's something else that we need to be aware of. So this isn't in the notes, but I think this is a better example than we have in the notes. So, okay, we will go ahead and start by saying that this 3x minus 5 over 2x plus 3 x minus 1 is equal to some constant over the 2x plus 3 plus some constant over the x minus 1. And then we'll get common denominators, which means this a is going to be multiplied by the other denominator, x minus 1. The b is going to be multiplied by the other denominator, 2x plus 3, and that equals 3x minus 5. So if I multiply this out, I get ax minus a plus 2bx's plus 3b equals 3x minus 5. And then gathering the x terms together, we have a plus 2b x's, and then a constant which is negative a plus 3b, and that equals 3x's plus a constant of negative 5. So my system would be matching the x's, a plus 2b equals 3, and negative a plus 3b would equal negative 5. If we add these together, we get 5b equals negative 2, so b is negative 2/5. And then back substituting a plus 2 times negative 2/5 equals 3. Let's multiply everything by 5, so it's going to be 5a. This is going to be negative 4 equals 15. So 5b equals 19, so a would be 19/5. And that means that this a is positive 19/5 over 2x plus 3. And then we've got negative 2/5 over x minus 1. So we would replace this integral with, let's see, there's going to be one integral for this. So let me move the 19/5 out here. And this is 1 over 2x plus 3. And we've got the negative 2/5 integral 1 over x minus 1. All right, so now, at this point, normally what we would just do is for this right, we would say negative 2/5, and this is just the natural log of x minus 1, and that's fine to do for that one, but I just wanted to point out something here. In this version, if we have anything multiplying this x other than just a 1, that means we should actually do the u substitution. Right? The u substitution here is 2x plus 3, which means the derivative of that would be 2, which means du is 2 dx, which means dx is actually 1/2 du. So we would have this 19/5 here, but when we replace this, this is going to be 1 over u, and this dx gets replaced with a 1/2 du. So there's a 2 that comes out here. And this is going to be a negative 19 over 10, and then 1 over u. So that means this first term is going to be 19/10, and then natural log of the u, which is 2x plus 3. And then we would still have our minus 2/5 natural log of x minus 1 plus c. So be careful. If there is a 2 here, You're also going to have to divide by that 2 when you do the natural log. So it is okay to, when you're evaluating this, 19/5 integral 1 over 2x plus 3, it is okay to just say, okay, it's that constant. It's natural log of 2x plus 3, but don't forget you have to divide by that 2. Okay. Here's another one. You can give this one a shot. Nothing particularly different about this, but one more to practice. I would factor, so x squared minus 3x minus 4. Does that factor into, let's see, minus 4 plus 1? Is that right? Minus 4 plus 1, yep. So we can write this as 6x minus 7 over x minus 4x plus 1. That's going to be a constant over the x minus 4, plus a different constant over the x plus 1. This one times this derivative, plus the b times the x minus 4. That's the derivative on that denominator, equals 6x minus 7. We multiply out here, we get ax plus a plus bx minus 4b equals 6x minus 7. Gather like terms. Ax plus bx is a plus bx's. Then we have an a over here for the constant minus a 4b equals 6x's plus a constant of negative 7. So a plus b would be 6. And a minus 4b would be negative 7. Maybe we can negate the top row, so negative a minus b equals negative 6, and then a minus 4b is negative 7, so when we add the a's cancel, we have negative 5b equals negative 13, so b is 13/5. And then if we plug in a plus b has to equal 6, that b is 13/5. Multiply everything by 5. 5a has to be 17. So a is 17/5. So this is 17/5 over the x minus 4 and 13/5 over the x plus 1. So this is equal to 17/5 over the integral of 1 over x minus 4. And 13/5 over the integral 1 over x plus 1. So that's going to be 17/5 natural log of x minus 4 plus 13/5 natural log of x plus 1, and then we tack on our sigma down. And this is about the level of work that we're expecting to see if you're showing work, like I have a free response question. All right. I think the only other thing I have here is just I'll walk you through one more complicated example, although this would be more difficult than you would see on our tests or on the AP exam. Let's say you had something innocuous, just integral of 1 over x cubed minus 1. Well, first, how would you factor that? Well, you could maybe guess that x minus 1 is a factor, and to find the rest, you could do something like synthetic division. You can say, put the 1 here, that makes this 0, and replace this with 1x cubed plus 0x squared plus 0x is minus 1. Bring this down, multiply, and then put this here and add. 1 times 1 is 1. Written there, add 1 times 1 is 1, add 0. This remainder is 0, which means the result is the polynomial 1x squared plus 1x plus 1. So it doesn't factor any further than that, though. Right? So unfortunately, we'll just have to say that this is equal to this. And that means we have two factors. One is linear, but one is quadratic, which means we're going to replace that with a over x minus 1, and then for this quadratic factor, we're going to do bx plus c. Then to get the common denominator, this side would have to be multiplied by this one's denominator, and this side would have to be multiplied by this one's denominator. And when you multiply out all of the numerators on the right side here, you get this, and just a 1 on the right side. Gathering like terms means you have some x squared terms, some x terms, and some constants. We have 0x squareds, 0 x's, and then a constant of 1. You can make a system by matching up the x squareds matching up the x's, and matching up the constants to get three equations for the three unknowns. Putting that into a matrix form for RAF would be the best way to solve for the three constants. You would have the three constants. And then you would plug those constants back in, here, here, and here, to replace the integrand with the result. So now the integrand would be this. And that means you could split this off, but each of these, we could write this as, if you brought the negative 1/3 outside, this is x plus 2 over x squared plus x plus 1. Now, what do we do for that? We could try completing the square. Actually, let's try that. If we have a non-factorable denominator, maybe we could try completing the square. Let's see if we could do that. Can we complete the square? X squared plus x plus 1. That would give me x plus a half squared. If I cut this in half, that would be a fourth, and then I can subtract the fourth there. Actually, that would work. And that would give me 3/4. So we could finish this problem with, no, I guess we still can't, because we have to have just a constant on the bottom. So never mind, we can't actually do that and get the arctangent form. I was thinking we can get the arctangent form, which is 1 over, if we had an integral of a u squared plus an a squared. But we're not going to be able to do that with this extra x. So what if we do if completion to arctangent doesn't work and you can't factor for partial fractions? Then you can do this tricky thing. You can say, if I was going to make a u substitution work, because it seems like this, if we made the denominator u, x squared plus x plus 1, the derivative would be 2x plus 1. So if I could get a 2x plus 1 on the top, u substitution would work. Now, if I decided to factor out this leading 2, that would be 2 times x plus a half. So I really needed x plus a half here. I have an x plus 2 currently. So what I could do is I could just add this plus half I need and subtract it back off to get this, and then split this into two integrals. One with the x plus 1/2 that I need for u substitution to work, and one with this constant, which turns out to just be, when you combine it, 3/2. And then this part here, we can make u substitution work. What will we do with this part? Well, we're going to do what we were getting ready to do over here. We'll do complete the square to arctangent form. So if you complete the square, you end up getting that this is x minus 1/2 squared plus 3/4. And that we can do a substitution where this x minus a half is the u, so du is dx, and this is the square root of 3 over the square root of 4 as the a, and write that in that form. Finally, when we handle the integrals, this one is going to be 1/3 natural log of x minus 1. This one's going to be a negative 1/3 natural log of x squared plus x plus 1. And then this is going to be the constant negative half, and then times 1 over a times the arctangent of u over a plus c. Right? So we won't encounter anything nearly this complex. But good to know how far these tools can be pushed. All right, that concludes both videos there for partial fractions expansion, the third most common procedure.